And again, we also know that the Helmholtz energy term, that is, so this is the Helmholtz energy term, that is A equals to U minus Ts, and differentiating this equation, we can write dA equals to du minus Tds minus SDT, and again if we put the value of du, Tds minus PdV, so here TDS will be cancelled out, and finally the value will be dA equals to minus PdV minus SDT. And similarly, we can write the value of dG equals to VdP minus SdP. So all the Maxwell's relationship will be derived from these fundamental equations. The first equation is dH equals to TDS plus VdP. The second one is this one, that is dA equals to minus PdV minus SdT. And similarly, the third one is dG equals to VdP minus SdT. So from these fundamental equations, we can derive the Maxwell's relationship. So if we start from this, starting du equals to TdS minus PdV. So this is equation 1.14. We have already discussed this equation in the last class. Now if we take the differentiation of this equation with respect to S at constant volume V, we can write del U by del S at constant volume V, which is equals to T. Because as we are taking the volume as constant, this term will become 0, and as we are differentiating this equation with respect to entropy, so the right hand term will completely become only T, and hence this is the differential form of equation 1.14. Now again, differentiating equation 1.109, this equation is 1.109. If we differentiate this equation with respect to V at constant entropy, that means again if we differentiate this equation with respect to V at constant entropy, we can write del by del V del U by del S at constant V so that means, so this is the LHS side, and if you take the differentiation of the LHS side with respect to V at constant entropy S, we can write the LHS like this, and the right hand side is nothing but only temperature. And if you take the differentiation of the RHS with respect to V at constant entropy, we can write the RHS as del T divided by del V at constant entropy. So this is equation number 1.110. And similarly, differentiating equation 1.14 with respect to V at constant entropy, so that means again if we differentiate this equation at constant V with respect to S at constant V, with respect to V at constant S, the value will that can be written as del U by del V at constant entropy equals to minus P. Because as we are taking the entropy as constant, this term will become 0, and again we are differentiating this equation with respect to V, so the second term will become minus P, and hence the final value will become this one, minus P. Now similarly, again if we differentiate this equation with respect to S at constant V, we can write, so here in this equation the RHS is like this, del U by del V at constant entropy, and if we differentiate the RHS with respect to S at constant volume V, the RHS will be like this, and similarly, the LHS will be like this, and similarly in the RHS side you will find minus P, and if you differentiate the RHS side with respect to S at constant volume V, we can write minus del P by del S at constant volume V. And again, since internal energy U is a state function, then using the Euler's relationship is valid, because we know that the Euler's relationship is valid for state functions, and this is the Euler's relationship. So using this Euler's relationship, so that is given in 1.113, So equation 1.113 is the first Maxwell's relationship. That means if you compare both the equations, you can see, so one equation is 1.112 and the another equation is 1.110. So if you compare both the equations 1.110 and 1.112, we can write del T by del V at constant entropy equals to minus del P by del S at constant volume. So this equation represent the first Maxwell's relationship. So this one is the first Maxwell's relationship. And similarly, we'll move to derive the other Maxwell's relationship. And again, we know that according to the Gibbs equation, TH equals to TDS plus VDP. And differentiating this equation with respect to pressure at constant entropy, we can write del H by del P at constant entropy equals to V. Because as the entropy will be constant, this term will become 0. And again, we are differentiating this equation with respect to P. So this will become VdP divided by dP, and finally that will, the RHS side will become P. Now this is equation 1.114. And again, further we will differentiate this equation with respect to entropy at constant P. That means we are differentiating this equation both times. So this equation is the derivative form of the Gibbs equation. So that is the derivative form of the enthalpy. That is dH equals to TdS plus VdP. So this equation is 1.104. We are differentiating twice. This equation 1.104. We are differentiating this equation two times. For the first time, we are differentiating the equation with respect to pressure at constant entropy. And for the second time, again we are differentiating the equation with respect to entropy at constant pressure. And finally, we will find this value. So similar type of derivation will be there. And this is known as equation 1.115. And similarly, the equation 1.104, if we again differentiating the equation 1.104, so here the base equation is equation 1.104, that is dH equals to TdS plus VdP. And again we are differentiating the same equation with respect to entropy, that means with respect to S at constant pressure B at constant pressure P, and the value will be del H by del S at constant pressure equals to T. As we are taking pressure as constant and we are differentiating the equation with respect to entropy, so the RHS side will become only T. And similarly, we have to differentiate this equation twice. First, we have differentiated the equation with respect to entropy at constant pressure, and then we have differentiated the equation with respect to pressure at constant entropy. And the final value will be like this. And again, enthalpy is a state function, and we can use the Euler's relationship. So from equation 1.117 and from equation 1.115, we can find out the second Maxwell's relationship. This one is the second Maxwell's relationship, that is del V by del S at constant pressure equals to minus of del T by del P at constant entropy. And again we will move to another two equations, that is dA equals to minus PdV minus SdT and dG equals to minus SdT plus VdP. And if we will differentiate these two equations according to the similar way, we can found another two Maxwell's relationship. So here, these are the four different Maxwell's relationship, and derivations of this Maxwell's relationship are one type of short questions so that you can find in your exam. So here we have discussed the four Maxwell's relationship and derivations of the Maxwell's relationship. You can find out the question like this. So here this is the question: derive the following expression for Maxwell's relationship using Gibbs equation and corresponding to Helmholtz equation. That means you have to derive this one. Now coming to Gibbs energy change for a reaction. Here Gibbs energy change is del G, but if the Gibbs energy change is considered for standard state, then the standard Gibbs energy change can be represented as del G naught. And mathematically, del G naught for any equation equals to del G naught of the product, summation of del G naught of the product minus summation of del G naught of the reactant. That means the standard Gibbs energy change for a reaction, that is del G naught, equals to total Gibbs energy total summation of Gibbs energy of formation of the product minus Gibbs energy of formation of the reactants. So then that will give rise to total Gibbs energy change of the reaction. For example, if we will consider one example, that is 1.15, calculate the standard Gibbs energy change for the following reaction at 300 Kelvin using the data given below. And here the equation is like this: glucose C6H12O6 that will undergo oxidation to form carbon dioxide and water, and some amount of energy will be released. And in this equation, the reactant side you will find glucose plus oxygen, in the product side carbon dioxide and water. So in the question it is given that the standard Gibbs free energy of formation of glucose, the value is given minus 913 kilojoule per mole. The standard Gibbs energy of formation of carbon dioxide is minus 395 kilojoule per mole. Similarly, the standard Gibbs energy of formation of water is minus 237 kilojoule per mole. And here the standard Gibbs energy of formation of oxygen is 0, because the Gibbs energy of formation of any elemental state, any element is considered to be 0. So oxygen is in the elemental form. So that's why here the standard Gibbs energy of formation of oxygen is 0. Now the question is, find out the standard Gibbs energy change of the following reaction. Here it is given the reaction, and according to the equation we know that the standard Gibbs energy change of any reaction equals to summation of Gibbs energy of formation of the product minus Gibbs energy of formation of the reactant. And here you can observe that in the product side 6 moles of carbon dioxide gas and 6 moles of water liquid are there. So the summation of Gibbs energy of formation of the reactant, first we will discuss the product. The summation of Gibbs energy of formation of the product equals to 6 into Gibbs energy of formation of water plus 6 into Gibbs energy of formation of carbon dioxide. Because in the product side you can observe 6 moles of water and 6 moles of carbon dioxide is there. So we have to multiply 6 into Gibbs energy of formation of water plus 6 into Gibbs energy of formation of carbon dioxide. And these value you can find out. So Gibbs energy of formation of water, that is given in the table, that is minus 237. And similarly Gibbs energy of formation of carbon dioxide given in the table, that is minus 395 kilojoule per mole. And hence the summation of Gibbs energy of formation of the product is minus 3792 kilojoule per mole. And similarly we will find out the Gibbs energy of summation of Gibbs energy of formation of all the reactants. So that is equals to Gibbs energy of formation of glucose. Here it is in the balanced equation, you can find 1 mole of glucose is there, in the equation 1 mole of glucose is there. So here the Gibbs energy of summation of Gibbs energy of formation of reactant equals to Gibbs energy of formation of glucose plus, and 6 mole of oxygen gases are there, plus 6 into Gibbs energy of formation of oxygen. And as oxygen is an element, its Gibbs energy of formation is 0, and the Gibbs energy of formation of glucose is given in the table. So the total value will become minus 913 kilojoule per mole. And hence, substituting all the values in this equation, that means summation of Gibbs energy of formation of product and also summation of Gibbs energy of formation of reactants, we can find out the standard change in enthalpy of the reaction equals to minus 3792 kilojoule per mole, minus 3792 kilojoule per mole, minus 913 kilojoule per mole, and that will become minus of minus, that will become plus, and this is the final value. And similar questions we can also solve from your material. So here it is given another question. So here enthalpy of formation and entropy of formation is there, and in this question Gibbs energy of formation of any substance is not given, but we can find out the Gibbs energy of change in Gibbs energy or Gibbs energy of formation equals to, that is del G naught equals to del H naught minus T del S. So using this equation we can find out the final value, that is del G naught value can be calculated. And this is another question. So these are very the question can be solved using the similar methods. So in this question, enthalpy of formation of the surreactant and products are given, and similarly entropy of the reactant and products are given. You can solve the questions in the similar way. Now coming to so these are some terminal questions are there. You can so here you can see derive the following relations using appropriate expression. So these are the Euler's, sorry, these are the Maxwell's. So from the Maxwell's relationship you can derive all these equations. Now coming to the next, so the next one is partial molar variable. Yes, the next one is partial molar quantities and their significance. So here, the effect of change in composition of any system on thermodynamic properties of the system. So here we will discuss the effect of change of composition of any system. That means if there will be change in composition of any component inside the system. And again we know that composition of a system comes into picture only when the system consists more than one substance. If the system will contain one substance, then the composition is 100%. If the system will contain more than one substance, suppose binary system or ternary system, then the composition term will arise. But if in the system only one component will be there, then there is no question of composition, because for one component the composition of that component is 100%. That means if the system contains more than one substances, that is two or more substances, then such a system having two or more substances, that is called a mixture. So here the partial molar quantities and their significance will be valid for mixtures only. Now coming to a solution having one solvent and one solute. So if we will consider a solution having one solvent and one solute, that means if in the solution two components are there, then that is called a binary solution. So when we will dissolve, example of such binary solution is if we dissolve sodium chloride in water, we get a binary solution in which the sodium chloride is the solute and water is the solvent. And if the solution having one solvent and two solutes, then that is called ternary solution. And similarly, if a solution contains one solvent and three solutes and all the solutes are soluble in the solvent, then that is called quaternary solution. And again, a solute and two immiscible solvent are also make a ternary solution. And the solute can be solid, liquid, or gaseous. And similarly, solvent can also be solid, liquid, and gaseous. And based upon the three combinations, we can found three different types of solute and three different types of solvent. We can find out 9 different types of binary solutions can be possible. A solution is formed by dissolving two solute, for example, sodium chloride and potassium nitrate in water. That is one example of ternary solution. That means a two solute and one solvent, so three component system. That's why that is called ternary solution. In case of both the components are liquid and the mixture is a, and if in case of both the components are liquid, the mixture is known as a solution if both the liquids are completely miscible. So that means if you take a mixture of water and kerosene, then that will not a solution. But if you take a mixture of alcohol and water, because we know that both alcohol and water can be soluble with one another in any proportion, so in that case, that is considered as a solution. And when the system consists two or more gases, it is known as a mixture of gases, because we know that if you take any gases at any proportion or at any pressure, so that will mix with one another to form the solution. A mixture of two gases is known as a binary mixture of gases. Now, to determine the various properties of the mixture, we need to know how many components are present in the mixture and what is the amount of each component. So that means here we want to know the amount of each component. So the amount of each component means we should know that the concentration of each component in the solution. In order to determine the concentration of the each component, so here we will discuss different concentration terms. In order to discuss the different concentration terms, first let us consider a binary solution. The first one is molarity. All these things so you have studied in your intermediate level. The definition of molarity is so it is defined as number of moles of solute per liter of the solution. That means molarity equals to number of moles of the solute divided by volume of the solution in liter. But if the volume of the solution is given in ml, so the equation can be number of moles of the solute into 1000 divided by V. So here V is considered in terms of ml. If V is considered, that means volume is considered in terms of liter, the equation will become N divided by V. So here Ni is the amount of component of the Ni of the component I in moles, and V is the volume of the solution in cc centimeter cube, that means ml. So here the volume is considered in ml, but if the volume will be considered in liter, the molarity will be number of, that is Ni divided by V. And similarly, another concentration term that is called molality, that is expressed in small m and is defined as amount of solute per kilogram of the solvent. That means molality equals to number of moles of the solute divided by mass of the solvent in kg. But if mass of the solvent is given in gram, we can write molality equals to number of moles of solute into 1000 divided by W. So here W is the mass of the solvent in gram. And hence, the unit of molality is mole per kg. And then coming to mole fraction. Suppose we will consider a binary mixture A and B. So the mole fraction of A can be written as number of moles of A divided by total number of moles of the mixture. And similarly, mole fraction of B can be written as the number of moles of B divided by total number of moles of the solution or mixture. So here Na moles of component A and Nb moles of component B mixed to form a solution. So mole fraction of A equals to number of moles of A divided by total number of moles, that is Na divided by Na plus Nb. And similarly, mole fraction of B is equals to number of moles of B divided by total number of moles, that is Nb divided by Na plus Nb. And if we will consider the binary solution, the total mole fraction of the solution will become 1. That is, the symbol of mole fraction is chi. So this symbol is known as chi, and in some book that is also written as x. So xa plus xb or chi a plus chi b equals to 1. And similarly, if we will contain a solution of three components A, B, and C, then chi A equals to number of moles of A divided by total number of moles, that is number of moles of A plus number of moles of B plus number of moles of C. Similarly, similarly mole fraction of B equals to number of moles of B divided by total number of moles, that is Na plus Nb plus Nc. And similarly, mole fraction of C equals to Nc divided by Na plus Nb plus Nc. In that case, mole fraction of A plus mole fraction of B plus mole fraction of C equals to 1. So here, if we take total fraction, just like so if we add a total percent, that will become 100. And similarly, for total fraction, the value will be 1. So these are the different concentration terms used to quantify the components in any solution, that is molarity, molality, and mole fraction. Now coming to the next one, that is called partial molar properties. So partial molar properties are considered for the extensive properties of a system. Partial molar properties are considered for extensive properties. So we know that all the thermodynamic properties are divided into two types. The first one is intensive properties, and the second one is extensive property. So first you should know what is intensive property. So the properties which are independent upon the amount of substance present in the system, that is known as intensive property. For example, temperature, pressure, so refractive index, magnetic property, magnetic moment, all these are dipole moment, all these are intensive property. For example, if you take 10 ml of water, its surface tension, whatever value, so that will come. And if you take in another system 100 ml of water, both having same surface tension. So surface tension is nothing but that is one intensive property, because that is independent upon the amount of the substance present in the system. But extensive property is dependent upon the amount of substance present in the system. So the partial molar properties are used for extensive properties of a system, because the extensive property of the system are the properties which are depend on the amount of the substance, that means depend on the number of moles of the system present in the number of moles of the substance present in the system. Now, if we divide such a property by number of moles, we will get the corresponding molar property, that is property per mole of the substance. For example, if we will consider examples of different extensive thermodynamic properties, we know that the different extensive thermodynamic properties are internal energy U, enthalpy H, and Gibbs energy G, volume V. So all these thermodynamic properties are extensive properties, because these properties are dependent upon the amount of the substance present in the system. So these properties, so these extensive properties are considered as X, and hence their molar value of the property X will be given by. So if you consider the molar value of volume, molar value of internal energy U, enthalpy. So if you calculate the value of these thermodynamic properties in terms of molar value, we have to divide the value of the thermodynamic property of the system divided by amount of the system in moles. So here, for example, if the volume of 1 mole of the substance, if we calculate the volume of 1 mole of the substance, that is known as molar volume, and hence molar volume can be calculated as total volume, molar volume Vm equals to total volume V divided by number of moles of the substance present in the system. So Vm equals to V divided by N. Vm is nothing but molar volume, and V is the total volume of the system having n number of moles, and here we are calculating what is the volume of 1 mole of the substance. So that is called molar volume. And similarly, we can calculate molar internal energy, molar enthalpy, molar Gibbs energy, etc. And partial molar properties are useful for all these extensive properties. Now, let us write the mathematical expression for the change of thermodynamic property X with change in composition of the system. And here we know that x means any extensive property. That means that may be volume, that may be internal energy, that may be enthalpy, that may be G, that may be U, that may be A, that may be B, whatever may be. So here we are considering the extensive properties to be X, and we know that X is a function of temperature, pressure, and number of moles present in the system. Why number of moles present in the system? Because we are considering this as extensive property. As this is extensive property, so this is a function of temperature, pressure, and N. So that is the property is a function of temperature, pressure, and N. Here X is said to be dependent variable which depends on the values of temperature, depends on the values with pressure, and depends with the values of number of moles n, and which can be varied independent each other and also called independent variables. So here T is independent variable, P is independent variable, and number of moles is also independent variable. But X is dependent variable because X is a function of T, P, and N. So that's why X is a dependent variable. So that is, here we are discussing the function of a dependent variable equals to function of some independent variables, temperature, pressure, and number of moles. So we can now here we have considered X as any extensive property. X is a function of temperature, pressure, and number of moles. And if you take the differential of X, that is dx, equals to partial derivative of X with respect to T at constant pressure and constant number of moles into dt. Similarly, plus, so that is dx equals to del x by del t at constant pressure and constant number of moles dt, plus del x by del p at constant temperature and constant number of moles dp, plus del x by del n at constant temperature, constant pressure dn. So in the first term, we have taken the differential of the RHS with respect to T at constant pressure and constant number of moles. In the second term, we have taken the differential of RHS with respect to P at constant temperature and constant number of moles. In the third term, we have taken the differential of X with respect to N at constant temperature and constant pressure. So where the first differential term, so that represent change in property X. So that means the first term represent change in property X, that is dx, change in property X when temperature of the system is changed, keeping constant pressure and constant number of moles. And the second term represent change of the property X as a function of temperature when pressure and N are kept constant. And similarly, the third term represent change of the property X with respect to change in number of moles, keeping temperature, pressure as constant. So this is equation 2.9. Now, in this equation 2.9, now if we'll extend this argument to a binary mixture. So here the equation is like this. So X is a function of temperature, pressure, and number of moles. And if we extend this argument to a binary mixture of two components A and B, where Na moles of A and Nb moles of B are present in the system, and we can write the value of X equals to function of temperature, pressure, comma Na, comma Nb. Where Na, where T, P, Na, Nb are the independent variables, but X is a dependent variable. And using the similar method what we have taken here, what if we take the differential of this equation 2.10, the differential will be like this. So here we are taking the differential of this equation 2.10. So that will become dx equals to del x by del t at constant pressure, constant number of moles of A, constant number of moles of B, dt. That means in the first term, we are only changing the temperature of the system, keeping pressure, number of moles of A and number of moles of B constant. Similarly, in the second term, we are changing the pressure of the system, keeping, so this term will be T. Actually, there is a printing mistake, so that will be T, right? So in the second term, represent change of X with respect to change in pressure of the system, keeping temperature, number of moles of A and number of moles of B as constant. Similarly, in the third term represent change of X with respect to change in number of moles of A, keeping temperature, pressure and number of moles of B as constant. Similarly, the fourth term represent change of X with respect to change in number of moles of B, keeping temperature, pressure and number of moles of A as constant. All of you understood? Hello?
Yes, sir.
Okay. And here we can note that the thermodynamic property X changes with the change in temperature, pressure, number of moles of A, number of moles of B respectively. Now, if we wish to change the property on changing Na and Nb while keeping the temperature and pressure constant, that means if we consider only the change in number of moles of A and change in number of moles of B, keeping the values of temperature and pressure as constant, as we are keeping the values of temperature, pressure as constant, so dt will be equals to 0 and dp will be equals to 0. Now putting the values of dt equals to 0 and dp will be equals to, that means if we consider constant temperature and constant pressure, the first and second term will be vanished, because at constant temperature dt will be equals to 0 and similarly at constant pressure dp will be equals to 0 and the first two terms will be vanished, right? So the value of dx, so that means at constant temperature and pressure we can modify the equation 2.11 like this: dx equals to del x by del na at constant temperature pressure nb dna plus del x by del nb at constant temperature pressure na dnb. And here the two terms in the RHS are the partial derivative of the properties with respect to number of moles of the component Na and similarly the number of moles of the component Nb. So these terms are known as partial molar properties. Here the first term of the RHS represent the partial molar property of the component A, while the second term of the RHS represent the partial molar properties of the component B. To understand the physical significance of the term partial molar property, let us consider a situation where we take large volume of a binary mixture and add 1 mole of a component A. Again, we are to understand the physical significance of the term partial molar property, let us consider a situation where we take a large volume of a binary mixture and add 1 mole of a component A. So that means we will take a large volume of binary mixture A and B. To that binary mixture, we will only add 1 mole of the component A. So the change in number of moles of A, that is DNA, in the solution will equals to 1. So this is because we have just added 1 mole of component A in the solution. So DNA equals to 1. Since we have taken large volume, the mole fraction of the component B practically does not change. As we have taken large volume of the solution A and B, so and to that solution we have added just 1 mole of A. So change in number of moles of A, that is DNA, equals to 1. And again, as the solution is having a very large volume, DNB is equals to 0. That means we have not changed the number of moles of B in the solution. So in that case, the equation 2.12 will become dx equals to del x by del Na at constant temperature, pressure, and constant number of moles of B. So thus the partial molar property of a component A in the mixture. So from this expression we can find out what is the definition of partial molar property of a component A. So thus the partial molar property of a component A in a mixture can be defined as the change in the property X of the mixture when 1 mole of the component A is added to large volume of the mixture at constant temperature and constant pressure, while keeping the amount of the remaining component constant. So that means change in property X, partial molar property of component A is defined as change in the property of X in the mixture when 1 mole of the component A is added to large volume of the mixture, maintaining constant temperature, constant pressure, and constant amount of other component except A, because we have added 1 mole of A. So the other components, the number of moles of other components will be constant. So this is the definition of partial molar properties. And the partial molar properties can be written as xi bar or xim, where I represent the component whose amount is being varied, and the subscript m represent, that is for molar, partial molar things, and a bar on the top of the symbol, that is the property, indicate the property to be also molar. So here you can write m or you can put a symbol bar, both having same meaning, that is the molar. Using such representation, we can write dx equals to xamDNA plus xbmDNB. So here xam is the partial molar property of A and xbm is the partial molar property of B. So here dx is the total change in property X due to change in composition at constant pressure and constant temperature. That means here the first term represent the total change in property when change in number of moles of A will be there, and the second term represent change in the property X when change in number of moles of B will be there. Now, using this above expression, so this expression can be applicable for any extensive property X. So using this expression, that is dx equals to xam DNA plus xbm DNA dnb, we can write the partial molar, different types of partial molar properties for a binary mixture. Now, if we'll consider, and if the thermodynamic property is volume, because here we will consider the extensive properties only. If the thermodynamic property will be volume, then the partial molar property term can be called partial molar volume, and V is a function of Tp. Here we are considering binary mixture, so V is a function of Tp, number of moles of A and number of moles of B, and the symbol for the partial molar volume can be written as Vi bar or Vim. And the expression, so this is the symbol of partial molar volume and this is the expression of partial molar volume. And similarly, if we will consider another extensive property, internal energy U, that is a function of T, P, Na, and Lb, and that is called partial molar internal energy, that can be represented as UIM or U bar I, and the expression can be given as like this. So the expression will be, this is the expression of partial molar internal energy. And similarly, if you consider another extensive property, enthalpy, that is a function of temperature, pressure, number of moles of A and number of moles of B, that is called partial molar enthalpy, that can be represented as HI bar or HIM, and this is the expression of partial molar enthalpy. Similarly, we will consider another extensive property, entropy, S, that is a function of Tp, Na, and Nb, that is called partial molar entropy, and the expression is SIM or SI bar, and the symbol is SIM and SI bar. So this is the expression of partial molar entropy. Similarly, Gibbs energy is also one type of extensive property. So the symbol is GIM or GI bar, and that is, and then the expression for partial molar Gibbs energy, that is del G by del Ni at constant temperature, constant pressure, and constant number of moles of J. And the expression is called partial molar Gibbs energy, and its other name that is called chemical potential, because Gibbs energy is very important thermodynamic parameter, because we have already studied in the last class. From the Gibbs energy we can find out the criteria for spontaneity of a process. So art, so this is very important parameter to find out the criteria for spontaneity of the process. The partial molar Gibbs energy is called chemical potential. So now, if we extend this, so here up to this we have discussed the partial molar terms for binary component. Now, if we'll extend this argument for a multi-component system, that means the system will contain Na moles of A, Nb moles of B, Nc moles of C, Nd moles of D, and so on. That is multi-component system. So if we extend the argument for a multi-component system, the thermodynamic property will also depend upon temperature. So this is the first dependence property, temperature, pressure, then number of moles of A, then number of moles of B, and then number of moles of C, and so on. So we can write x equals to function of T, P, Na, comma, Nb, comma, dot, dot, and so on. And now, so this is for the, so this is the value of any extensive property for a multi-component system, for a mixture of multi-component system, or for a multi-component mixture. So x equals to function of the value of the extensive property depends upon temperature, pressure, and number of moles of each component. So in the previous section we have derived the values for binary system, and here we are considering the multi-component system. So similarly we can write for any infinitesimal change, and if we take the derivative term, so this is the value of x, and if we take its differential form, dx equals to del x by del t at constant pressure, constant Na, constant Nb, constant Nc, and so on dt. And that means the first term represent change of the value of x with respect to change in temperature, maintaining the other parameters constant. Other parameter means pressure, number of moles of A, number of moles of B, number of moles of C, and so on. And the second term represents the change in the value of x with respect to change in pressure only, maintaining, and here again some typing error is there, so that is t will be there in place of p, you should write t. So here this term represent the change in value of X with respect to change in pressure at constant temperature T, constant number of moles of A, constant number of moles of B, and so on. And similarly, the third term represents the change in values of X with respect to change in number of moles of A at constant temperature, constant pressure, constant NB, constant NC, and so on. The next term represent the change in the values of X with respect to change in number of moles of B at constant T, constant P, constant Na, constant Nc, and so on. And similarly, somewhere the last term will be like this. This term represent the change in values of X with respect to change in number of moles of the ith component at constant temperature, constant pressure, constant number of moles of A, constant number of moles of B, constant number of moles of C, etc. So, and again, if we will maintain under condition of constant temperature and constant pressure, so if we will take the total expression into constant temperature and constant pressure condition, so the dt value will become 0, the first term will vanish, the dp value will become 0, then the second term will vanish, and the final term will become at constant temperature and constant pressure, the final term will become, so here we are taking the value of dx at constant temperature and constant pressure, the final term will become dx equals to second term, sorry, dx equals to third term plus fourth term plus ith term and so on. That means first term and second term of this equation cancelled. So using the representation of partial molar quantities, because we know that this term is nothing but XAM, partial molar quantities with respect to change in number of moles of A. So this equation can be written as dx equals to XAM DNA plus XBM DNB plus XIM DNI and so on. So this is the change. So this equation represent the change of value of the partial molar quantities at constant temperature and constant pressure for multi-component system. Now coming to relationship between thermodynamic properties and partial molar properties. Here we will discuss the relationship between thermodynamic properties and partial molar properties. And here we know that the mole fraction of a component A in a mixture can be written as, that is, XA equals to number of moles of A divided by number of moles of A plus number of moles of B. That is the number of moles of that is Na divided by Na plus Nb, and which is equal to Na divided by N. N means total number of moles, that is also equal to Na plus Nb, and implies that Na equals to mole fraction of A into total number of moles. Here N equals to summation of the number of moles of B, that is the total number of moles, and similarly we can write Nb equals to mole fraction of B into total number of moles. And similarly, to keep the composition of the mixture constant, so if we want to keep the composition of the mixture constant, that means the percentage of each component will become constant. That is, Na and Nb should be changed in such a way that Xa and Xb do not change. That means if you will add both A and B with equal proportion, so that Na in the mixture will change, Nb in the mixture will change, but Xa and Xb will remain constant. Now let us increase the total amount of A and total amount of B. So that is the total amount Na plus Nb from n moles to kn moles. And if we change the number of moles of A as DNA and change the number of moles of B as DNB, we can write DNA equals to mole fraction of A into Dn, and DNB equals to mole fraction of B into Dn. So here Dn is change in total number of moles of the mixture or solution. So DNA equals to mole fraction of A into Dn, Dnb equals to mole fraction of B into Dn, and hence again Dn equals to Kn minus n, so which is equals to n into K minus 1. Here Xa and Xb are not changing while the changing the amount of A and B. So that means here we are observing that we will add A and B will equal proportion, so that number of moles of A and number of moles of B in the mixture or in the solution will change, but the mole fraction will not change. And if we substituting the value of DNA and DNB in equation 2.14, so this is the equation 2.14 for binary solution. This is the equation 2.14 for binary solution, because we have already discussed that dx equals to XAM DNA plus XBM DNB, and this equation derived at constant temperature and constant pressure. As we have considered constant temperature and constant pressure, the first two terms cancelled out. So the first term cancelled and the second term cancelled for constant temperature and constant pressure. So we will finally found the equation 2.14, that is dx equals to partial molar properties of A into DNA plus partial molar properties of B into DNB. Now, if we use this equation 4 here, equation 2.14 here, we can, if we use the values of XAM, if we can replace the values of DNA and DNB in that equation 2.14, we can write dx equals to XAM into chi A, Dn chi A is mole fraction of A, plus XBM into chi B Dn, that is equation 2.24. Now to find the total values of A, equation 2.24 need to be integrated from the amount n of the mixture to final amount Kn. So that means the total number of moles of the mixed, the total number of initial moles is n and the total number of final moles is Kn. Since x is an extensive property, the n changes by k times and x will also change by k times. Therefore, if we take the integral of this equation 2.24, so the LHS side you can find, that is the integration of dx from ax to kx. In the RHS side you will find integration of RHS from an to kn. So this is integration of n to kn, because the total number of moles of the mixture changes from n number of moles to kn number of moles. K times increase is there. So integration of RHS with respect to n to kn, that is, so we will find the total change of property x with respect to change in number of moles of A and change in number of moles of B. So from this equation, we have changed the composition in such a way that the mole fraction of the two components do not change. That means the initial mole fraction of component A and component B is also the final mole fraction of component A and component B. So from equation 2.25, we can write, so we will take the integral of that. So we can write kx minus k. You can see this one, because we know that integration of dx is x, and here the limit is the upper limit is kx and the lower limit is x, so the value will be kx minus x. And if we'll go to the right hand side, the upper limit is n and the upper limit is kn and the lower limit is n, and the values of the right hand side, and here XAM. So here we have taken the condition that number of mole fraction of A will remain constant and mole fraction of B will also remain constant. So and the partial molar properties of A, mole fraction of A, partial molar properties of B, mole fraction of B, all are constant. And hence, so the RHS of this equation 2.25, this term of RHS of equation 2.25 will remain constant, and that will be out of the integral. And here you will take the solution of RHS will only the integration of dn, where the upper limit is kn and lower limit is n. And simplifying this equation, we can write x whole into k minus 1 equals to xam mole fraction of A, xbm mole fraction of B, and if we take integral of dn with upper limit with lower limit n and upper limit kn, the value will be kn minus 1, kn minus n, and again we will take n as so that will become k minus 1 into n. And substituting the values of xa and xb and simplifying, if we substitute the values of xa and substitute the values of xb again and simplifying, finally we can write x equals to partial molar properties of x, partial molar properties of A into number of moles of A, plus partial molar properties of B into number of moles of C. And similarly, if we extend this argument to multi-component system, then x equals to summation of partial molar properties of ith component into mole fraction of ith component. So that is 2.29. Now coming to partial molar volume. So first we will discuss the partial molar volume properties. And we know that the volume is an extensive property. So the total volume of a binary solution depends upon temperature, also depends upon pressure, depends upon amount of substance A, and also depends upon amount of substance B. Here we are considering binary solution. That is, V is a function of T, P, Na and Nb. Now again using equation 2.12 at constant temperature and constant pressure. If so, there we have written dx. Here we will write V in place of x. So x means any extensive property. Here we have taken the particular extensive property V. So V is a function of T, P, Na and Nb, and if you take differential of V, that is dV, at constant temperature and constant pressure, the value will become like this. First we will take dV. Just wait 1 minute. So yes, so here we have taken volume. So volume is an extensive property. So V is a function of temperature, pressure, number of moles of A, number of moles of B. So here we are considering binary mixture. So V is a function of temperature, pressure, number of moles of A and number of moles of B. And if you take the differential dV equals to del V by del T at constant pressure, constant number of moles of A, comma, constant number of moles of B dt. The second term will become del V by del P at constant temperature, constant number of moles of A, constant number of moles of B dP. The third term will become del V by del T, del V by del Na at constant temperature, constant pressure, constant number of moles of B dNa, and the fourth term will become del A, del V by del Nb, del V by del Nb at constant temperature, constant pressure, constant number of moles of A dNb. And if we will consider the total condition at constant temperature and constant pressure, the first term will become 0, the total term will become 0, and the second dP will be 0, so the total second term will become 0, and the final term will become like this. So the first and second term will be vanished, so the final term will dV at constant temperature and constant pressure, dV equals to del V by del Na, constant T, constant P, constant Nb dNa plus del V by del Nb, constant T, constant P del Na dNb. So the differential term will be like this at constant temperature and constant pressure. So again we will move to the note. Here you can find this one, del dV equals to del V, this term we have derived. So this is equation 2.31, and here this term of equation 2.31 is called partial molar volume of A, and this term of equation 2.32, equation 2.31 is called partial molar volume of B. So that means we can put x m x v vma for this in for this term in equation 2.31, and for this term we can put vmb. Now suppose we add 1 mole of component A to the mixture at constant temperature, constant pressure without changing the number of moles of B. So in that condition DNA will be equals to 1. That means change in number of moles of A will be equals to 1, and change in number of moles of B will be equals to 0. So this equation, so this equation will become dNb will be 0, and hence the second term will be completely 0, and hence the final equation will become dV equals to del V by del Na Tpnb. So this expression provides us the definition of partial molar volume, and here this is the definition of partial molar volume. Exactly similar definition we have derived for partial molar property. So here the same definition is applicable for partial molar volume. Now using the notation of partial molar properties, we can write dV equals to VAM dNa and VBM dNb. And similarly the total volume of a binary mixture when, so this is the total volume of a binary mixture when Na moles of component A are mixed with Nb moles of component B at constant temperature and constant pressure, and the expression can be given by taking differential by taking integration of equation 2.33. So that will become V equals to VMANA plus VBMNB. So this is about partial molar volume. So the partial molar volume term for B can be written as VMB equals to del V by del NB at constant temperature, constant pressure and constant number of moles. Now coming to at 25 degrees Celsius and 1 bar pressure, the molar volume of pure, so here we will take one example. So in this example, suppose at 25 degree Celsius and 1 bar pressure, the molar volume of pure water means the volume of 1 mole of pure water, that is called VMA star, that is equals to 18.07 cc per mole or 18.07 moles ml per mole. And similarly, the partial molar volume of pure methanol is 40.07 ml per mole. That means the volume of 1 mole of pure water is 18.07 ml centimeter cube, means that is cc, that is ml. So the volume of 1 mole of pure water is 18.07 ml, and similarly the volume of 1 mole of pure methanol is 40.75 ml. When we mix 100 ml of water at 25 degrees Celsius and 100 ml of methanol at same temperature, it is found that the total volume of the resulting mixture is not 200 ml, rather that is 1.93.1 ml and not equal to. So here we have taken a mixture of 100 ml of pure water mixed with 100 ml of pure methanol at 25 degrees Celsius, and you will find that the resulting mixture will not 200 ml, rather that will become 193.1 ml. So why this is happening? Because when we mix water with methanol, so the interaction of water and water, if we individually consider the interaction of water and methanol is greater than the interaction of water and the interaction of methanol and methanol. That means the interaction of water and methanol in the solution is greater than the interaction of water molecules in pure water, and also the greater than the interaction of methanol molecules in pure methanol. And hence, as the interaction of water and methanol molecules is more than the individual interaction in the solution, so the total volume of the resulting mixture decreases. It is not 200 ml, it will become 193.1 ml. So let us calculate the composition of the mixture first. So here we have taken 100 ml of pure water mixed with 100 ml of pure methanol. So VA is 100 ml, that means VA star, that is 100 ml, and VMA, that is molar volume of pure water. Molar volume means volume of 1 mole of pure water. So here the total volume of the pure water added. So that is VA star. VA star is 100 ml and VMA star is 18.07 ml. So number of moles of A equals to 5.53 mole. And similarly, if you calculate the number of moles of B, that will become 2.45 moles, and the mole fraction of B, that is equals to NB by Na plus Nb, that is 2.45 divided by 5.53 plus 2.45, and the mole fraction of B is 0.307, and if you calculate the mole fraction of A, that is 1 minus 0.307, we will find out the value of Xb or mole fraction of B. If we prepare a mixture by mixing 5 ml of water and 5 ml of methanol, that is 50 times the volume used in the above case, the volume of the mixture will be 50 times, that is 9.655 ml, and it will have the same mole fraction of methanol, that is 0.307. So initially we have added 100 ml of water and 100 ml of methanol. We will find the mole fraction of methanol is 0.307 and the mole fraction of water is 1 minus 0.307. And similarly, if we use 5 ml of water with 5 ml of methanol, exact similar mole fraction we will find. So on adding 40.75 ml of pure methanol to the above solution, it is observed that the volume of the solution increased only by 38.8 ml. So if we add 40.75 ml of the pure methanol to the above solution, the volume of the solution will increase by only 38.8 ml. Similarly, on adding 1 mole of pure methanol to the solution prepared by mixing 10 ml of water and 10 ml of methanol, also the volume increased by similarly 38.8 centimeter cube. So now let us calculate the mole fraction of this solution, and so that is compared in the table 2.2. In that, so the overall conclusion of the part is like that. So if you increase the volume of the solution or decrease the volume of the solution without changing the number of moles of each component, without changing the mole fraction of each component, then the total volume of mixing will remain same, whether that is used for 100 ml of solution or that is for 50 ml of solution. And here we will find the molar volume of B. So the molar volume of B, that is equals to del V divided by del NB. So if we will divide the number of moles of B, we will find the molar volume of B. So one question is there, so that can be calculated using this equation. V equals to VMW NW plus VMM NM. So here NW is number of moles of water and NM is number of moles of methanol, and VMW is the molar volume of water, VMM is the molar volume of methanol. So you can directly put the value. And similarly, the second question can also be solved by using this expression. So here VMM, that is the molar volume of methanol, VMW molar volume of water in the solution, VMM molar volume of methanol in the solution, but VMM star molar volume of methanol individually, and VMW molar volume of water, molar volume of pure water. VMW star is the molar volume of pure water, VMM star is the molar volume of pure methanol. And here VMM is the molar volume of methanol in the solution, VMW is the molar volume of water in the solution. We can solve the equation also. Now coming to volume of mixing. So volume of mixing is nothing but del V, that is del V mix or del mix V, right? So here we are calculating the volume of mixing, because if you will consider two liquids A and B and let 100 ml of A is mixed with 100 ml of B, then the solution will be equals to 200 ml only when if the interaction of AB is equals to interaction of AA and interaction of BB, then the solution will become 200 ml. But if the interaction of AB is greater than the interaction of individual A and interaction of individual B, then in the solution more interaction will be there, then the volume of the solution will become less than 200 ml. And similarly, if the interaction of AB is less than the individual interaction of A and also less than the individual interaction of B, then the volume of the solution will be greater than equals to 200 ml. So if the volume of the solution will be equals to 200 ml, then that is called ideal solution. So for ideal solution, change in volume of mixing, that is del mix V or del V mixing, will be equal to 0. That means there will be no change in volume after mixing the two different solutions. The two different components A and B to make the solution, there will be no change in volume. So del V mix will be equals to 0. If the solution will be ideal solution, then del V mix equals to 0. But if the solution will be non-ideal solution, then del V mix will not be equals to 0. So the non-ideal solution is again divided into two types. So the non-ideal solution where the interaction will be more than the individual interaction, then the volume will decrease, and another type of then the volume will decrease, then negative deviation will be there, and another type of non-ideal solution where the interaction of the two components A and B is less than the individual interaction AA and individual interaction BB. In that case, the total volume of the solution will be greater than that obtained from ideal value, and that is called positive deviation. So here, so these are the graphs that are describing the positive deviation and negative deviation from the ideal value. So here, this is the dot. So the dotted line represent the molar volume of the component. So here, the left hand side of the equation represents only B. Then the left hand y-axis of this graph represent only B, and the right hand y-axis represent only A will be there. And from if you move from left to right, mole fraction of the A increases from left to right. So the extreme left hand side where the mole fraction of A equals to 0 and mole fraction of B equals to 1. That means the left hand side axis completely represent for only B, and the right hand side axis represent only A is there. And if you move from left to right, the mole fraction of A, that is chi A, increases from 0 to 1. And suppose you will take any middle point here. So this point represent 0 point. So this point so represent a mixture containing A and B, where mole fraction of A is 0.4 and mole fraction of A is 0.4 and mole fraction of B is 0.6. Now this is the dotted line represent volume of the solution A and B if the solution is an ideal solution. But as we have stated that the solution is non-ideal solution, that means if the interaction of AB in the solution is less, so the interaction of if the interaction of AB is less than the interaction of individual AA or the interaction of individual BB, then inside the solution the interaction is less, so the volume of the solution will quite increase from the ideal value. Ideal value is the dotted line. And similarly, if the interaction of the solution AB is greater than the individual interaction of AA and individual interaction of BB, then the volume of the solution will decrease as that of the pure component A and B. So this is called negative deviation, and here this is called positive deviation. So positive deviation will be there if the interaction of the two component is less than the individual interaction, and negative deviation will be there for the volume if the interaction of each component is more than the individual interaction of A and B. Now coming to experimental determination of partial molar volume. So the partial molar volume can be experimentally determined using these graphs. If the graph will be a straight line, then you can easily put y equals to mx plus c graph. So from that value, so you can find out the values of partial molar volume. But if the graph will be a curve like graph like this, if positive deviation or negative deviation will be there, so in that case you have to take tangential value. So from the tangential value you can calculate the partial molar volume. Now coming to the next important property, that is called chemical potential. So the chemical potential is nothing but partial molar Gibbs energy. So as the Gibbs energy is important parameter to find the criteria of spontaneity of a process. So here we will discuss the partial molar Gibbs energy, and also the partial molar Gibbs energy is known as chemical potential. So the partial molar energy is also important in study chemical equilibrium and also phase equilibrium. Due to the importance of partial molar Gibbs energy in thermodynamic studies, it was given a special name that is called chemical potential. And in the previous section, we have discussed about the partial molar volume, and here we will discuss partial molar free energy. So partial molar free energy is free energy is G. So partial molar free energy is nothing but del G by del Ni at constant temperature and constant pressure and constant number of moles of J, and that is known as chemical potential mu. So the partial molar free energy is known as chemical potential. Its symbol is mu. So mu I equals to del G by del Ni at constant temperature, constant pressure, and constant number of moles of other component except ith component. So thus the chemical potential of the ith component, that is mu I, refers to the rate of change of Gibbs energy will change in number of moles of the ith component when temperature, pressure, and the number of moles of all other components kept constant. Again, we will go to the definition of chemical potential. So the chemical potential of the ith component mu I refers to the rate of change of Gibbs energy with change in the number of moles of the ith component when temperature remaining constant, pressure remaining constant, and number of moles of the other component except ith component. Then the number of moles of the other component except ith component will kept constant. So this term derived nothing but from the x, what we have discussed here. So here so all the derivation we have discussed for x. X means any extensive properties. X means any extensive properties. So now in place of x we are considering the energy. Just previous section we have discussed, in place of x we have taken partial molar volume, and here in place of x we are taking partial molar free energy. So this is the partial molar free energy, nothing but the chemical equation. So this term represent the chemical potential. This term represent the chemical potential, that is called mu I. So this is the chemical potential of ith component of a solution. So in the chemical potential part, another one long question is there, that is called Gibbs-Duhem equation, that we'll discuss here. As discussed, Gibbs energy G depends, because this is an extensive property. G is an extensive property. So the Gibbs energy G depends upon temperature, depends upon pressure, and also depends upon composition. So if you consider a binary mixture A and B, so the G equals to function of T, P, Na, and Nb. Now, if you take the differential of this term, dg equals to del G by del T at constant pressure, constant Na, constant Nb dt, plus del G by del P at constant temperature, constant Na, constant Nb dP, plus del G by del Na at constant temperature, constant pressure, Nb dNa, plus del G by del Nb at constant temperature, constant Na dNa. Na dNb. So this is the differential of Gibbs energy term. And from the previous unit, we know that del G by del T at this is nothing but minus S, and similarly this term represent V. So the equation 2.50 can be written. So and also here this term represent chemical potential of term A, that is mu A, and this represent mu B, and this one represent minus S, this one represent V. This is the chemical potential of A, that is mu A, and this term is the chemical potential of B, that is mu B. Putting all the values, you can write dg equals to minus sdt plus vdp plus mu A dna plus mu B dnb. Now, if we'll take this expression at constant temperature and constant pressure, then del T dt will become 0, dt equals to 0, and dp equals to 0. So this term will become 0, this term will become 0, and the first two term vanishes. So we will find dg equals to mu A dna plus mu B dnb. This expression gives the change in Gibbs energy with the change in composition of a binary mixture at constant temperature and constant pressure, because initially we have considered constant temperature and constant pressure condition. Now, if we write using equation 2.2 for x, what we have discussed for x. So in the equation 2.28 represent the equation for x, and here we are replacing the x by g, that is the total Gibbs energy in a binary mixture can be written as. So that means if we take integration of this, we can just write g equals to mu a na plus mu b nb. This gives the Gibbs energy of a binary mixture at a fixed temperature, that means constant temperature, constant pressure, and constant composition. For a pure component, we can just write G equals to mu A plus mu A Na, because pure component means only one component is there, only A is there. So G equals to mu A Na. And similarly, we can write mu A equals to G divided by Na. Now coming to the significance of chemical potential. So this is a theoretical term because chemical potential is very significant, because that is the partial molar free energy, and we know that free energy is the measure of that is a very important thermodynamic property, because that is describes the criteria of spontaneity of a process, and all the naturally occurring processes are spontaneous. So that's why gives free energy, gives energy, that is g term is very important term, and as g term and as the g is an extensive property, so that depends upon the amount of the substance present in the system. So chemical potential is also very important thermodynamic parameter. Now coming to effect of temperature and pressure on chemical potential. So first we will discuss the effect of temperature on chemical potential, and here we have defined the chemical potential mu I equals to del G by del Ni at constant temperature, constant pressure, and constant number of moles of other component except ith component. Now differentiating this equation, exactly similar differentiation term will be there what we have done for x. So differentiating this equation, we can write this, and again according to the Euler's theorem and extractness, so we can write so using Euler's theorem, so this equation 2.58 changes into equation 2.59, and again we know that del G by del Ni at constant pressure, constant number of moles of I, constant number of moles of J, that is equal to minus S. So therefore this equation del mu I by del T at constant P, constant Ni, constant Nj is equal to this term, and similarly that is equal to this and this. So so this type of equation we have derived using x, and here we are deriving using g. So the final value of the chemical potential of the ith term can be obtained by integrating the above equation from lower limit mu I at temperature T1 to mu I at temperature T2, and similarly in the RHS term we'll take the integration of the SIM, that is the molar entropy of ith term, that is SIM dt, from temperature T1 and T2, and if we simplifying this we will find the value of this one. Now coming to effect of pressure change in chemical potential. So exact similar Euler's theorem will be there. According to the Euler's theorem, we can find out so d mu I equals to partial molar volume of ith component into dp. Now coming to mixture of gases. So if you consider for mixture of gases, similar derivation term will be there, and what we have derived for component X, and for ideal gas. Yes. Now coming to the next equation, that is called Gibbs-Duhem equation. So that is one long question. As we have already discussed that the change in any extensive properties at constant temperature and pressure. So at constant temperature and pressure, dt value will be equals to 0 and dp value will be equals to 0. So the change in any extensive property X at constant temperature and pressure is given by dx equals to xma dna plus xmb dnb. So here xma is partial molar properties of A, and XMB is partial molar property of B, and DNA is change in number of moles of A, and DNB is change in number of moles of B. So initially we have derived this expression also. Now, whereas the total extensive property, so here this is the infinitesimal change of the extensive property X, that is dx. Now, if we will consider the total value of the extensive property at constant temperature and constant pressure, we can take the integration of this equation 2.24, and taking the integration of this equation, we can write x equals to xma na plus xmb nb. And again, if we take the differential of this equation 2.28, that is dx equals to xma dna. So here the value is xma na, x equals to xma. Xma means partial molar value of A, and Na is the number of moles of A. XMB is the partial molar any extensive property B, and NB is the number of moles of B. Now if you take the differential of this equation dx equals to xma dna plus na dxma plus xmb dnb plus nb dxmb equation. So this will give rise to equation 2.88. And again, since both equation 2.24 and equation 2.88 are same, here equation 2.24, here this is the value of dx. And if we compare both the equations, we can see equation 2.24 is dx equals to xma dna plus xmb dnb. Equation 2.88 is dx equals to xma dna plus na dxma plus xmb dnb plus nb dxmb. That means these two terms, the addition of these two terms equals to this term plus this term equals to 0. If we compare equation 2.24, equation 2.28 with equation 2.88, we will find the value of xma dna plus xmb dnb equals to 0. And hence, simplifying this value, we can find na dxma plus nb dxnb equals to 0. This is equation 2.90, and this equation 2.90 is the integral form of very important relation that is known as Gibbs-Duhem equation. So this is a very important question for your term and examination. Gibbs-Duhem equation. And hence the Gibbs-Duhem equation can be written in terms of volume. Here we have taken the Gibbs-Duhem equation in terms of any extensive property X. Now if we write the Gibbs-Duhem equation in terms of volume, that can be written as Na dV Ma plus Nb dV Mb equals to 0. And similarly, again we can write Na dV Ma is equals to minus Nb dV Mb. This relationship implies that for a binary solution, for a binary system, the partial molar volume of a component cannot change independent of the partial molar value of the other component. If the partial molar value of a given component is increased by some method, then the partial molar volume of the second component will be decreased. So here in this equation you can see NaDm NaDVMA equals to minus NbDVMB. That means the partial molar volume of a component cannot change independently. So if the partial molar volume of a given component will be increased by some method, then the partial molar volume of the second component will be equally decreased. Thus, this is true. This is true for all type of partial molar quantities, not only for partial molar volume. So this equation is true for all type of partial molar properties, and hence the Gibbs-Duhem equation in terms of so as this is valid for all type of extensive properties or all types of partial molar properties, and this equation in terms of chemical potential, if we write the Gibbs-Duhem equation, we can write Na d mu A plus Nb d mu B equals to 0. So this is the Gibbs-Duhem equation in terms of chemical potential. If the changes in temperature and pressure are also considered, then the Gibbs-Duhem equation in terms of chemical potential is. So here we will consider the changes of temperature and pressure. But if we consider at constant temperature and constant pressure, then the Gibbs-Duhem equation in terms of chemical potential can be written like this. But if we consider the Gibbs-Duhem equation of chemical potential when the temperature pressure are not constant, then the Gibbs-Duhem equation can be written as minus SdT plus VdP plus Na d mu A plus Nb d mu B equal to 0. Now coming to so here there are two questions. So the first question is for a binary mixture where Na equals to 3 Nb. If the chemical potential of A changes by 2 joule per mole, what is the change in chemical potential of B? So this equation can be solved by putting direct values on the equation solved. Now, so these are some terminal questions. So you can easily solve these questions. So these are theoretical questions. Define partial molar properties, and here calculate partial volume of water in an equimolar mixture of ethanol and water. So this all these solutions we have discussed. Now coming to the next part, the next one is introduction to statistical mechanics. So up to now we have already completed the general classical general thermodynamic part. So after that we will discuss about the statistical thermodynamic part. So in the statistical thermodynamic part, we have to consider the permutation combinations things will be there. So this statistical thermodynamics we will discuss tomorrow. So if you have any type of doubts, you can ask. Hello, all of you understood or not?
Yes, sir.
So in the general thermodynamics, here you can see what are the expected questions for general thermodynamics. So I will tell the expected long questions in the general thermodynamic part. So expected long questions we will start from starting. You can see. So this is Helmholtz function, and after that, yes. So the first one is Helmholtz function, and the second one is Gibbs function, and there are two expected short questions, two expected long questions are there. That is criteria of spontaneity and equilibrium in terms of Helmholtz energy and Gibbs energy. So there are two questions: criteria of spontaneity in terms of Helmholtz energy and Gibbs energy, and then we will move to another two long questions are there. So the another two long questions are Gibbs Helmholtz equation in terms of Gibbs energy and Gibbs Helmholtz equation in terms of Helmholtz energy. So two different give the two different forms, derivation of two different forms of the Gibbs Helmholtz equation. And after that, so the Maxwell's relationship, derivation of the Maxwell's relationship is another long question. And then the next one is partial molar property. Yes, Maxwell's relationship, another long questions. So you will find the four different Maxwell derivation of the four different Maxwell's relationship applying the derivative term. And next one is the give del G naught, that is the standard Gibbs energy change for any reaction del G naught. And from this part you will find numerical questions. So very easy numerical questions are there, because del G naught of any reaction equals to summation of Gibbs summation of Gibbs free energy change, summation of Gibbs free energy change of the product minus summation of Gibbs free energy change of the reactant. So numerical questions will become from this part. And after that, the next expected long questions, that is called partial molar properties. So in the partial molar properties, so you will find the first one is partial molar quantities and their significance. So here molality, mole fraction, and molarity. So short questions will be there. Then coming to partial molar property, significance of partial molar property, and then chemical potential and its significance, and variation of chemical potential at constant temperature and constant pressure, and Gibbs Duhem equation. So these are the expected long questions, and the statistical thermodynamics part we will discuss tomorrow. Okay. Hello.
Yes, sir.
Okay.
Thank you.